The second example, we're just going to look at the same two reservoirs connecting by two pipelines, two series pipeline. We have some more specifications about that, the levels. So the difference in level Z between the water surface of reservoirs in this example is 53 meters. So the difference between point A and point B is 53 meters. And the pipelines, both pipe 1 and 2 are 1 kilometer in length. Pipe 1 has a diameter of 0.3 meters, and pipe 2 a diameter of the 0.6 meters. So the friction factor lambda 1 for pipe 1 and lambda 2 for pipe 2 are both the same, is equal to 0.04. So the question here is to evaluate losses and calculate the discharges. The discharge, we have like only the one discharge. So once we're just going to have like a difference level and a pipeline, obviously the flow discharge from the upper reservoir to the lower reservoir. So we need to just calculate what is the rate of the flow and the head losses. As you know better, the head losses happens from like a point A down to like the point B. And we just analyzed in the previous examples, it happens at point, it's because of one, because of the like the entrance head loss, minor head loss, because of the friction head loss of pipe 1, dropped by amount of 2, and then dropped by amount of 3 because of this kind of like expansion between the two diameters, and then pipe number 4 in here, and eventually pipe number 5 at the end in here. So all of them together, we need to just calculate in here. So how we're just gonna do this one? To just calculate this one, what we normally do is that we can just write the Bernoulli's equation between 2 points, which is point A and point B. So if you're just gonna write the Bernoulli's or energy equation between 2 points, intentionally the water surface level is chosen at two reservoirs. So obviously the pressure head is like the atmospheric pressure, so it's 0. And the velocity head for both points exactly at the water surface are 0. So the velocity and the pressure head is 0. If the elevation or the reference line is chosen exactly at the water surface of the low reservoir, you can see here, for example, if I can draw like the line here. So obviously ZA, so ZA, the level here, is equal to Z, or the difference of the level between two reservoirs, that is given to us 53 meters. So that is for ZA. And for ZB, obviously, because the datum or reference line is chosen at the water surface of the second or low reservoir is 0. So as a result of that, so if you're just going to write the Bernoulli's equation, all terms are 0. On the left-hand side, we have Z. And on the right-hand side, we have all the like the pressure, velocity head are 0, and elevation head is 0. And the only terms left is all the energy head losses. So all the energy head losses include entrance losses or head loss, friction head loss of pipe 1, expansion head loss between the two pipes, and a friction head loss in pipe 2, and exit head loss because of this like exit point here that we have. We learned before that the entrance head loss is half times of the velocity at the pipeline. So it's like a half V1 squared over 2G. V1 is like the velocity of the pipe 1. Friction head loss is the lambda 1 L1 L1 V1 squared over 2G D1. And expansion loss, we learned before that is the difference of the velocity. The expansion between two pipes is like the velocity, is the difference of the velocity in two pipes, V1 minus V2 squared over 2G. Friction head loss in pipe 2 is a lambda 2 L2 V2 squared over 2G D2. And exit head loss is equal to the 1 times of the velocity, V2 squared over 2G. Let's just have a look at the exit head loss and the entrance. Why the entrance head loss is like a half times V1 squared over 2G, and the exit like a V2 squared over 2G. Just have a quick look at this. So if you just remember, we can just get back here. This is the entrance. If you have like the system like this one, remember we discussed it before for shape B. So we have like the sharp H and the KL, or the minor head loss, that we're just going to use it here, or the coefficient like the half times the V squared over 2G. So the entrance head loss is like the half times V velocity at this point squared over 2G. And for exit point, remember, it's regardless of the type of the like the exit, or the type of the like the round, or the H. So all of them, the KL or the coefficient is like the 1. So it's a 1 times V squared over 2G. So that's the reason for the exit is like the 1 times of the V squared over 2G. But for entrance, if it's like the sharp H, it's like the half times. So we assume that is like the half times, and that's the reason that we can have this one in this shape as like the half times. Okay, so if we're just going to substitute all the figure that we have is given to us, so we can have, so first of all, we want to just have like a relationship between V1 and V2, because in this equation, we have two unknown variables, V1 and V2, we don't have any of them. But by using the continuity equation, we can just use this one. Continuity equation is really useful equation that all the time, once we have like a changing in the like the diameter of the pipe, we can just use that one and connect and relate the different velocities to each other. So we can write V1A1 is equal to V2A2, or if we rearrange A to one side, we can just calculate V1 as is equal to A2 divided by A1 times V2. And you know, the A can be written as like the pi d squared over 4, and the pi can be for both sides A1 and A2 can be cancelled, and the same for 4. So we can easily write A2 over A1, we can just easily write D2 squared over D1 squared, or the ratio of the D2 over D1, all inside the bracket raised to the power 2. So the V1 is equal to the ratio of the D1 over D2, D2 over D1 raised to the power 2 times V2. So if we have like the diameter here is given to us, D2 is 0.6 and D1 is 0.3, and raised to the power 2, and this ratio is like the 2, 2 to the power 2 is like a 4. So V1 is simply calculated, V1 is equal to 4 times V2. So if you're just going to substitute V1 is equal to 4 times V2 in this equation, and if you can just put all like the other like the parameters, substitute the parameters like the lambda, L, and V, and D, we can easily calculate, and also we know the Z as well, we can easily calculate the V1 here. So let's just see. So we're just going to put everything here, and the only unknown variable is like a V2, because if we can substitute V1 with like a 4 times V2. And we can have on the left hand side 53, on the right hand side we have like a 1, 2, 3, 4, 5 terms, and the result is, I mean, if you're just gonna sum up all the 5 terms, is like equal 113.049 V2 squared, and V2 squared is like is equal to 0.4688, and if you just square root from both sides, V2 is equal to 0.685 meters per second. So that is the example. That's the result of like a section 2, but we need to just calculate the V1, and you know the V1 is equal to 4 times V2, which is equal to 2.74 meters per second. And the discharge is also needs to be calculated based on the continuity equation. We can just write like the A1 V1, or we can just use A2 V2, doesn't matter. So we're just going to use A1 V1. A1 is like a pi 0.3 squared over 4 times 2.74, and the result is 0.194 cubic meters per second. So, and by the way, we can just calculate all like the head losses should be equal to the difference between two levels. So we have all the terms: entrance, friction in pipe 1, pipe 2, and expansion and exit head loss. All of the terms is like a coefficient of the like a V1, or either V1 or V2. We can substitute all of them in here, and all the terms, this one, this third, fourth, and fifth, the sum of all these terms together is equal like a 52.997 meters, so which is really equal to the like a 53 meters. But if you can carefully look at these all these 5 terms, interestingly, you can see this term or the friction loss in pipe 1 can contribute almost most of the most of the values here. For example, if I'm just gonna calculate I'm just gonna see how much percentage is made up for the friction in pipe 1 is like the 59.74 divided by let's just use it 52.997 and times 100. So you can see here 96% of the total head loss is lost in friction head loss, friction loss in pipe 1. You can see here how big it is. And after that, the second the losses is like the friction loss in pipe 2 is like the 1.5 meter. But you can see how big it is compared to like even pipe 2. But the reality is that the pipe 1 is only, the diameter is only half of the pipe 2. Just bear in mind, if you use like a very small pipe, how big you might just lose your energy head loss. And the other like the minor head losses, you can see how small they are. Like all of them are definitely less than 1. Like the first one, 0.2, and the second expansion is like more or less similar, and exit head loss is really, really small. So this is the example 2.